Now that we've compared passive and active remote sensing systems, let's look at some of the most widely used Earth observation satellite programs and see which types of sensors they carry and the kinds of data they collect. So this is lecture 4B on major Earth observation satellites. Okay, so on board the satellites are sensors. So they're instruments that detect and measure electromagnetic radiation reflected or emitted from the Earth's surface. Examples include Operational Land Imager, otherwise known as OLI-2 sensor. So that sensor could be aboard Landsat 9, the sensor platform. And another sensor could be the Thermal Infrared Sensor, which is TIRS, on Landsat 8 and 9. And so the key idea here is that a satellite could be a platform and the sensor is the instrument collecting the data. And so one of the most important Earth observation programs ever developed is the Landsat program, which we've already looked at in labs week 1 and 2, I believe. And it began in 1972 as a partnership between NASA and the U.S. Geological Survey with the goal of continuously monitoring the Earth's surface over time. Landsat uses passive optical sensors, meaning it measures sunlight reflected from the Earth's surface. And because of this, Landsat collects imagery in multiple portions of the electromagnetic spectrum, including the visible, near-infrared, and shortwave infrared wavelengths that we've been discussing over the past 2 weeks. One of the Landsat's greatest strengths is its long historical record. So since satellites have been collecting data for more than 50 years, scientists can compare images from different decades to study changes in, forests, cities, glaciers, coastlines, etc. And then most Landsat imagery has a 30-meter spatial resolution, meaning each pixel represents an area approximately 30 by 30 meters on the ground. The satellite revisits the same location every 16 days, making it well suited for monitoring long-term environmental change. And last week, you used Landsat imagery to create true color and false color composites. Now you know more about the satellite platform and sensor responsible for collecting those images that you worked with. The next satellite program is the Sentinel program. Sentinel-2 is what we're going to be looking at. And it's the world's most widely used Earth observation program. It's the Copernicus Sentinel program, developed by the European Space Agency, the ESA. There are multiple Sentinel satellites. The one we're going to discuss in today's lecture is Sentinel-2. So unlike Landsat, which is a US mission, the Sentinel satellites are operated by Europe as part of the Copernicus Earth Observation Program. Rather than having a single satellite, the Sentinel program consists of several satellite missions, each designed for a different purpose. So for this course, we'll focus primarily on Sentinel-2, which is an optical satellite similar to Landsat. And then later we'll discuss Sentinel-1, which uses radar, which is a different type of sensor. Sentinel-2 is a passive remote sensing system, meaning it measures sunlight reflected from Earth's surface, and it collects imagery in 13 spectral bands, allowing scientists to study vegetation, water, soil, and urban environments. One advantage of Sentinel-2 over Landsat is its higher spatial resolution. So several of its bands have a resolution of 10 meters, meaning 1 pixel equals 10 meters by 10 meters on the ground. And that single pixel contains all of the reflected energy from that 100 square meter area. The satellite cannot distinguish objects smaller than approximately 1 pixel. And then compared to Landsat's 30-meter resolution. So it's higher resolution than Landsat. This means that Sentinel-2 can capture finer details on the ground, making it especially useful for mapping agricultural fields, monitoring vegetation, studying land cover. Another advantage is its more frequent revisit time. So with 2 Sentinel-2 satellites in orbit, most locations on Earth are imaged approximately every 5 days. So that's more than the approximate 16 days from Landsat. You have already worked with Sentinel-2 imagery in Project 1 using the Copernicus browser. When you compared the true color and false color composites, the images you analyzed were collected by the Sentinel-2 satellites. So hopefully that makes a little more sense now. Now you could see how the satellite platform itself influences the quality and frequency of the imagery you were working with. And so far, we've looked at Landsat and Sentinel-2, both of which are passive optical satellites. But what happens if there's cloud coverage in the area that you want to image? Or like, say you need data at night. That's where an active sensor would come in handy. So that's where Sentinel-1 comes in. Instead of measuring reflected sunlight, it uses radar to actively illuminate the Earth's surface, so kind of acting like a flashlight, making it one of the most versatile remote sensing satellites available today. And so we have a set of images here on this slide. And in the image on the far left is an image collected by Sentinel-2, which is a true color optical image. I know it's a little blurry for us, but it's collected using a passive sensor, which means it's measured sunlight reflected from the Earth's surface. And you can recognize familiar features like green vegetation, gray roads, brown soil. And then on the right are images collected from Sentinel-1, which uses active sensor collection. And so this image was collected by Sentinel-1, and it actually used an active synthetic aperture radar, otherwise known as SAR satellite, which we'll talk about SAR in another lecture. But instead of measuring reflected sunlight, Sentinel-1 transmits microwave radar pulses and measures the energy that is reflected back to the satellite. We call that backscatter. The bright white areas in these images represent strong radar reflections, and then the dark gray areas indicate weak radar reflections. And so notice that the buildings don't appear in natural colors. They appear bright or dark depending on how they reflect radar energy. So the far right panel image, Sentinel-1 HH, is another radar image, but with a different polarization. So you have VV and then HH. Radar satellites can transmit and receive microwaves in different orientations called polarizations. Different polarizations emphasize different surface characteristics. For this class, we aren't going to focus on polarizations. Just know that they're there and they're different polarizations. The main focus from this slide is that Sentinel-1 on the right uses an active sensor, and then Sentinel-2 uses the passive sensor. And they also have different revisit times. They have different orbit heights, orbit inclinations, and different resolutions as well. The Sentinel-1 mission is also part of the European Space Agency's Copernicus program, but unlike Sentinel-2, it uses a completely different type of sensor. So instead of collecting reflected sunlight, it actually carries a synthetic aperture radar, or SAR, which is an active remote sensing system. Because Sentinel-1 generates its own microwave energy, it can collect imagery day or night and is able to image through cloud, smoke, and light rain. This makes it especially valuable for monitoring natural disasters and other situations where optical satellites may not be able to capture clear images because of those atmospheric conditions. So Sentinel-1 has a spatial resolution of approximately 10 meters, which is comparable to Sentinel-2 for many applications. However, instead of measuring color or reflected light, it measures the strength of the radar, right? So the radar signal that's reflected back from the Earth's surface is what it's measuring. And as a result, Sentinel-1 images appear in shades of gray rather than natural colors like we saw in that last slide. So because radar interacts differently with various surfaces, Sentinel-1 is commonly used to monitor floods, sea ice, ground deformation, landslides, earthquakes, and maritime traffic. And scientists also use Sentinel-1 to detect subtle changes in the Earth's surface over time that may not be visible in optical imagery. And so although Sentinel-1 and Sentinel-2 belong to the same satellite program, they provide different types of information. So Sentinel-2 helps us identify land cover, whereas Sentinel-1 allows us to observe Earth's surface under nearly all weather conditions using microwave radar. And there's a 6 to 12 day revisit time. and it does have a 10-meter spatial resolution. So together, these two satellites provide complementary data sets that improve our understanding of the Earth's changing environment. So they complement each other. The final satellite program we'll discuss uses MODIS, which stands for Moderate Resolution Imaging Spectroradiometer. MODIS is a passive sensor developed by NASA and is carried on two Earth-observing satellite platforms called Terra and Aqua. For example, someone might say, I downloaded MODIS imagery. So what they really mean is I downloaded imagery collected by the MODIS sensor aboard the Terra or Aqua satellite. This shorthand is common in remote sensing, just like people often say, I use Landsat imagery, even though the imagery is collected by the OLI-2 and the TIRS-2 sensors on Landsat 9. So just some jargon I wanted to bring up. And so unlike Landsat and Sentinel-2, MODIS was designed to provide frequent global coverage rather than highly detailed imagery. So the Terra and Aqua satellites together are able to observe nearly the entire Earth's surface every 1 to 2 days, making MODIS one of the most valuable sensors for monitoring changes on a global scale. So one important trade-off is spatial resolution. MODIS images have a spatial resolution ranging from 250 meters to 1 kilometer approximately, which is much coarser than a Landsat 30 meter or a Sentinel-2's 10 meter resolution. This means MODIS cannot distinguish individual buildings, roads, or small agricultural fields, right? It's a global scale. However, because MODIS images the Earth so frequently, it is extremely useful for monitoring just the large-scale environmental process, tracking wildfires, drought conditions, snow and ice cover, things like that. Think of MODIS as a global monitoring system, while Landsat and Sentinel-2 provide detailed images of specific locations. So MODIS allows scientists to observe broad patterns and changes across continents and even the entire planet. So imagine you're standing outside at night. If you simply look around using available light, you're acting like a Sentinel-2, which relies on reflected sunlight, which uses a passive sensor, right? But if you shine a flashlight and observe what reflects back, you're acting like Sentinel-1, which provides its own source of illumination. So the flashlight allows you to see even in the complete darkness, just as Sentinel-1 can collect data at night. So that's an active sensor. This is a helpful chart in just kind of wrapping up what we discussed. But basically the key takeaways is that there's different satellites and sensors for different purposes. And so you have to understand your objective in order to decide what satellite platform and sensor you want to collect images from. There's no one size fits all satellite and sensor type, right? It's depending on your project. Sentinel-2 tells us what the Earth's surface looks like. Sentinel-1 tells us how the Earth's surface interacts with microwave energy. So together, these complementary data sets provide a much more complete understanding of our planet. And so following this short Lecture 4B, please watch the supplemental videos. The links are provided on the Week 4 homepage before proceeding to the knowledge check and then this week's lab activity. Thanks.